We talked last time about flames, and we mentioned that pure oxygen flames have 10 times the heat intensity of the same flame burning in air. And that's because the combustion intensity is the product of the enthalpy of the reaction, or basically the temperature of the flame, and the velocity of the flame, the rate at which it brings the heat to the surface. And that basically makes it, the heat and combustion intensity, proportional to the temperature of the flame squared. Okay. If I have 80% nitrogen as bag heat, which just has to be heated up by burning in air, I will have a drop in flame temperature of about 2/3, something on that order. I also have a drop in PdV work, which is what gives me the velocity of the flame. It's the expansion of the gas. It gives me the velocity. And 3 times 3 is 10, right? Or thereabouts. So basically, a flame burning in air may have a temperature of 1,000 degrees C or 1,800 degrees F or even 2,200 degrees F. It's all approximate in all this stuff. But nonetheless, by all that extra nitrogen, you reduce the heat intensity significantly. Most of the flames we use in welding are pre-mixed. If we look at the torches, whether it's the little propane torches I passed around the other day, where you basically just have some holes in a venturi, and the tube itself is the mixing chamber, or whether it's an oxy-acetylene torch where you basically turn on a fuel valve and an oxygen valve, and then you have a mixing chamber, and then you go through the tube. Doesn't really matter. They pre-mix and get something close to the right stoichiometry. And in fact, in an oxy-acetylene torch, you can play with you shouldn't play too much with the acetylene pressure. The acetylene pressure should be roughly constant at about, if I remember correctly, about 5 psi. And you should, anybody know how much you open a fuel gas valve? I mean, if I'm turning on the gas in a tank, or even on the torch, do you screw the valve all the way open, or do you just open it a half a turn, or you open it 10 turns, or 5 turns? A quarter turn to a half a turn. And the reason is you want to be able to shut it off quickly. You don't want to have to sit there and crank the thing 10 turns while something else is burning up. Okay, if you want to shut it. So that's the general rule on fuel gas cylinders or torches, is the fuel gas only gets open a quarter to a half turn. And that usually will allow enough to flow through. Argon tank or an oxygen tank or other type, well, actually oxygen tanks are probably the same kind of partial turn. Argon tanks, on the other hand, you're supposed to open them all the way, which might be 6 or 7 turns. And the reason is they have a seal to close. They also have a seal at the top of the valve so that you don't leak oxygen impurity or air impurity in to the top of the valve when the valve is open. So basically they have a seal at the top, and you're supposed to open it all the way to the top to seal the top so that something doesn't leak into the valve while the gas is going out, because you're trying to get good pure argon as opposed to something contaminated air. The other thing, anybody else? What about the threads on fuel gas? Anybody know what they do for safety on the left-hand threads? In that way, it's impossible to hook the oxygen and the fuel up to the same system, because you can't screw things together. You can't screw right-hand threads and left-hand thread systems together, because what would happen if you did? You'd end up with a little bomb somewhere, right? And people have done that in the past, which is why the standard is the left-hand thread. And you know how you can do, well, on most cases, the left-hand thread you can tell, because on the hexagonal nut, they basically put a little groove, they machine a little groove in there to remind you that it's a left-hand thread. I guess I should have brought one or something, but if you look at an oxy-acetylene torch setup, it'll be a left-hand thread, but the nuts will also have a little groove just machined through the middle of the hex, okay, so that you can hopefully remind you why it's not screwing on properly when you turn it with the right-hand thread. And the last thing we said was the gas boundary layer greatly limits the heat transfer to the surface. I can be bringing in the equivalent of 100,000 watts per square centimeter to the surface, but the actual amount that gets into the material is only 2 to 10% of that, depending on the velocity of the gas and the temperature of the gas and whatnot. And the reason for that is I get this stagnant gas layer, the gas boundary layer, and I have to conduct the heat through that stagnant layer. It's basically an insulating layer on the surface of the gas, or on the surface of the solid, or the liquid that I'm trying to heat. Okay? We talked about the flames in general, only have heat intensities down in the 10 to the third watts per square centimeter range. I put that up, that plot up again. The oxy-acetylene flames are down here, but we're going to talk about later how we get to arcs, and how arcs are essentially a type of flame that I can get an extra order of magnitude for an open argon arc. I can get an extra order of magnitude, and essentially it's a trick to get away get around the boundary layer problem. In addition, today we're going to talk about flame cutting. In flame cutting, I actually get around the boundary layer problem, and I actually can get heat intensity equivalent to about 100,000 watts per square centimeter. So there are ways around these limitations on flames, and we'll talk about those in just a little bit. But there's also a debate among people who sell gases about whether you should use acetylene or argon for welding of steel, or which one you should use for cutting. Remember, acetylene is just two triple bonded carbons with two hydrogens. It's as simple a hydrocarbon as you can get, or the smallest number of atoms that you can get in a hydrocarbon. Even methane has got 5 atoms, CH4. The 80 bag flame temperature, that's if you burn it in pure oxygen with absolutely the right stoichiometry, is 3,100 degrees C. There's no heat loss to the surroundings. You'll get 3,100 degrees C. MAP, on the other hand, which is a registered trademark, stands for methyl acetylene propadiene. This is propadiene, which is 3 carbons with double bonds between the carbons, and then you fill in with the 4 hydrogens, so it's C3H4. That's all review. And methyl acetylene, you can have a methyl group over here, CH3, and there's your triple bonded carbon, and that's your acetylene with the methyl group on the end. Turns out MAP gas, because it's got, well, it has more hydrogens, and hydrogen doesn't burn as hot as carbon. It has a slightly lower 230 degrees centigrade, approximately 80 bag flame temperature. Now, if you listen to a MAP gas salesman, he'll tell you that MAP is safe. It can be pressurized. You don't have to fill up the tanks with acetone to dissolve the acetylene. You can handle it. It's lighter because of that to transport. It's safer, and it works just as well. And the question is, does it work just as well? Well, it turns out if the temperature of the flame, or the heat intensity, goes to the temperature of the flame squared, and if I'm trying to melt steel, the temperature difference of interest that I'm interested in is the melting point of that weld pool, or the temperature of that weld pool, which is about 1,600 degrees centigrade, and 3,100 minus 1,600, that quantity squared has units of 225 times 10 to the 4th. 2870 minus 1,600 has value of 161 times 10 to the 4th. So even though there's only a 8% difference in the 80 bag flame temperatures, of course that's degrees centigrade, not degrees Kelvin, but you can figure that's probably a 7% difference in degrees Kelvin or something. It turns out there's a 50% improvement, or 36% decrease, if you will, in the heating value of acetylene versus MAP if I'm trying to melt steel. If I'm just trying to heat up cold steel, there's hardly any difference at all, because it's going to be 3,100 minus, what, 20 degrees C. versus 2870 minus 20 degrees C, and you square those and there's not a big difference. But when you start trying to heat up something that's already hot, namely the liquid weld pool, your ability to transfer more heat into the molten weld pool is limited by the upper temperature of the gas that you're trying to use, and so that small difference in temperature has a big effect on your ability to weld. If you're using oxyacetylene, you can probably weld about 30% faster in terms of traveling along the weld pool as you can with gas. So why does anybody use MAP? Aside from the fact that you can buy these nice little handy cylinders like I had, you can burn down your house easier.
Cheaper.
It's cheaper. No, it's actually not cheaper. It's competitively priced. The main reason is it's safer. It really is safer. And for other applications, like flame cutting, it turns out you don't need that extra difference in temperature. It's not going to have a big effect. So let's talk a little bit about flame cutting, which is the next topic. Oxy-acetylene cutting. An oxy-acetylene cutting process, how many people actually, you saw the demo you saw it. How many people had ever seen it before that? Okay, so a lot of you have seen it. What's the biggest thing anyone's ever seen? Anybody seen 10-inch thick flame cut pieces? What's the biggest thing anybody seen? 3-inch? 4-inch? 1 inch? Okay. 1 inch, 1 or 2 inch. Well, the biggest I've ever seen is about 10 feet. Okay? 10 feet.
Thick?
Yeah, thick.
Steel?
Steel. Well, we're going to talk about it. It turns out steel is, it's not the only thing that can be flame cut, but it's one of the only things that can be flame cut. It turns out that flame cutting really is sometimes called burning of the steel, and it literally is oxidation of the iron. And the heat is coming from pure oxygen hitting the hot iron surface, and we'll talk about how you get around the boundary layer problem. You get tremendous heat intensities, and as long as you can blow a jet of oxygen into the hole, you can cut things that are very thick. And in fact, some of you have seen, if you're here in the second half, where I've shown you in a continuous cast in a steel mill, you have a hot band of steel coming out of the casting furnace, and they basically just take a pure oxygen lance. They don't even have a flame around. They just hit it with pure oxygen, and they just cut through it. And so you can cut through, you can certainly cut through 10 inches. They do that regularly on a continuous casting line for steel plate. You probably have 10-inch thick slabs. And they just, when it comes out, it's still at 1300 degrees C or something. They just hit it with oxygen, and the torch travel, the continuous casting line is the strand is moving very slowly. Well, the torch just moves with it. It's on a little carriage and cuts across this way, and you cut off a slab. Okay, it doesn't take very long to do it, as you saw in the demonstration. Actually, you also saw plasma cutting. Did you see how they show you oxyacetylene and plasma in the demo? Okay. Turns out plasma is becoming more popular for some reasons we can talk about. But for 100 years, oxyacetylene was kind of the way to go. It turns out people can take whole ingots in steel mills, and maybe I haven't seen 10 feet, I've seen 6 foot. Okay? Just take a whole ingot and just cut through it, if you got a big enough torch. And you're wearing all kinds of heat-resistant clothing and stuff. Okay, so what you do typically, the torch for oxyacetylene, schematically, is very simple. I'm going to have a central jet that will contain pure oxygen. I'm going to have some outside jets, which will be oxygen fuel mixture pre-mixed. So initially, this is my, we'll call it steel right now, my steel plate, and I will start some little flames, pre-mixed flames, shooting out here. I want to turn my oxygen on yet. If I look down on the, or end on the tip, here's my central oxygen hole, and I'll have a series. It can be 4, it can be 6, it can be depending on the size of these things. Obviously, if I'm cutting something 6 inches thick, I have a bigger torch, and I have a lot bigger oxygen center jet, and so I'm going to have more circles of these little flames around here. So these are the little pilot flames, if you will. The pilot flames will, if it's oxyacetylene or oxymat, will have, and it doesn't have to be, you can use oxypropane, or you can use oxy-gasoline. People use gasoline sometimes because it's a nice, simple liquid. You don't have to pressurize things. Basically, what you have to do, the flames might be a 1/4 inch long, and it'll be kind of a soft blue here, and it'll be a deeper blue, or actually kind of white internal cone. This is the primary combustion cone, and this is the secondary. In the primary, you're burning your oxygen with C2H2 or C3H4 or whatever it is your hydrocarbon is, and you're getting primarily water vapor and carbon monoxide. In the secondary combustion zone, you're actually getting a little bit of air come in here, and your CO is going to be burned to CO2. Carbon monoxide forms at high temperatures, CO forms at lower temperatures. So you have a hotter internal cone and a cooler outer cone, primary combustion of what's coming in your premixed flame, and then you use up all your oxygen, and then this outer cone is a secondary, the secondary combustion is basically sort of a diffuse flame, but it's very controlled diffusion, and so we don't call it a diffuse flame. It's not wisping around, it's got high velocity as well as the center. So that's what the torch looks like. This is the surface of your steel, or your titanium, or whatever it is you're going to cut. And typically I kind of come down when I'm doing cutting, oxy-acetylene cutting, and I put this inner primary flame right on the surface, just little points of those little things right on the surface of the steel. And then you kind of watch the surface of the steel until it starts to glow a little bit red. You're holding one spot, you see it glow red, and then you kind of see, I kind of look for a little specular reflection, kind of something kind of blowing back at me a little bit. And that basically is the oxide surface of the steel. This is an oxidized surface of the steel. The oxide starting to break up. It turns out for steel, the melting temperature is 1380 of the oxide. So it turns out for iron, T melting of the oxide versus T melt of the metal. For iron, it's 1380 degrees centigrade and 1536 centigrade. So the iron oxide surface layer here on the steel melts at a lower temperature. It turns out it's Oxide FeO. This is the black oxide on the surface. Same stuff as this. But as you heat it up, the oxide will expand on the surface. It will start to eventually crack up a little bit, and that's what's giving me some of this little specular reflection. As soon as I see that, the torch has got a trigger on it, and I open up the trigger, and the oxygen blows through, and now through these little cracks in the oxide, I'm putting pure oxygen in contact with hot iron as it breaks through the iron oxide, right? I'm breaking up these little islands of iron oxide, and I have pure iron underneath at 1300 degrees centigrade. In the presence of pure oxygen, I get ignition. I burn the steel. The iron becomes the fuel for that central oxygen jet. At that point, I can turn off these things, and I can keep burning with just a straight oxygen jet. Now, it turns out for hand torch cutting, you tend not to turn off these things, because the rate at which you can move forward, if you're just straight oxygen cutting, is only proportional to the rate at which the heat is transferred to the material ahead of you. So these are basically little preheating torches. Okay, so I ordinarily keep those on, but if my steel was already hot, like in a steel mill, I just cut with a straight oxygen torch. I don't have to do it. Okay, just the oxygen hitting the hot iron oxide. And you really don't have to get to quite 1380. Turns out this stuff breaks up. But once you do get ignition, this does get to 1380, just because of the heat of combustion of the reaction. You've got iron plus 1/2 O2 goes to FeO, plus lots of heat, and that melts. That heat melts the FeO. The gas jet blows the liquid oxide aside, exposing more fresh iron to a fresh oxygen jet, and you just burn right through it. And as you probably saw, you can punch through 1 inch of steel in a fraction of a second in this thing. So it's a very rapid process. It's basically a flare going off, but it's a controlled flare. So if I want to see what a flame cut surface looks like, turns out these are all plasma cut. But this is a handy dandy plastic standard for the American Welding Society for surface roughness guide for oxygen cutting. And there's sample 1, 2, 3, and 4. Sample 1 is someone who either has Parkinson's disease or probably was drinking too much the night before. Sample number 4 is a fairly flat, relatively smooth surface. I've seen things better than this, but basically, American Welding Society sells this so that a welding inspector can go through the shop, and if they've called out a specific level of quality of the cut, it's just a comparative gauge. But for you, it's just a little plastic mold. I'm sure those plastic molds were made from real pieces of steel. Okay, so far as that goes. Now, it turns out there are other metals that you can flame cut. Well, actually, there are not. But you can flame cut iron, and that's good. Aluminum, it turns out, we have some problems. And the melting temperature of aluminum oxide is 2000 centigrade, and the melting temperature of the aluminum is 661. You cannot flame cut aluminum. What will happen is you'll melt the aluminum underneath before the oxide breaks up and exposes fresh aluminum. That's not to say that aluminum metal can't be ignited, but it won't be ignited in a nice controlled way with the torch. You'll have a very serious fire as far as that goes. So that doesn't work. Magnesium is about 2800 C and 660 or 650 melting point of magnesium. So that can't be cut. Chromium, turns out, is about 20. Actually, it says 2800. I don't think that's right. I think it's 2200 and some lines. What's sublimation versus melting? Go directly from solid to vapor. No liquid in between. Dry ice sublimes. Solid to vapor, no liquid unless you're under high pressure. Chromium, as you heat up, the solid just starts to vaporize away. You don't get chromium liquid unless you go to high pressures. Turns out, oh, I'm sorry, that was right. There's 2800 for the chromium metal, I'm sorry. Or chromium oxide. It's 1875 for the metal sublimes. And so that means that stainless steel cannot be flame cut because it has a chrome oxide layer on the surface. And so you've got to have something that has a lower melting oxide, except titanium, 1750 for the oxide, 1668 for the metal. Turns out titanium can be flame cut. And the reason it can be flame cut is that above 900 degrees centigrade, titanium diffuses away the protective titanium dioxide scale. It will essentially, the oxide scale will dissolve away into or the oxygen will dissolve into the titanium. So it is possible to flame cut titanium. If you'd like to see a piece of flame cut titanium, this is the only one I could find in my office. But I don't know, you can look through your office to see if you have one. This actually is, for me, a historic piece. This was my first research contract when I became an assistant professor 25 years ago. But basically, there's a polished edge, there's two saw cut edges, but back here on the back side, you'll see a darker edge, and you'll see the same type of surface roughness. That's a flame cut titanium edge. That's 1-inch thick plate. Flame cut's just fine. The only problem is it tends to give off lots of smoke. And in fact, one of my stories I like to tell is this is before my office was right across from the lab. I was up on the fourth floor, and there was a particular staff member who will remain nameless, but used to complain about the smells coming out of the weld lab sometimes, you know, because you're actually in there welding and doing things, any kind of metal shop where you got flames and torches, and we have exhaust fans, and you turn them on, and they just go right out the window. But in any case, this was 15, 20 years ago, and the technician at the time was named Bruce. And Bruce was flame cutting some titanium for some of the work we were going to do, and does a lot. I mean, even though the ventilation was on, the whole place kind of gets a little hazy and stuff. And so the person across the hall smelled it and called the safety office. They called me before, and I said, "Oh, okay. You know, this is weeks before when we were doing it some other time." I said, "Oh, okay." You know, I just kind of ignored them, right? So they called the safety office. So the safety office comes over, and Bruce is in there, and they come in and see all the haze in the air, and say, "Bruce, what's going on here?" He says, "I'm flame cutting titanium." And the guy says, "What kind of lab is this?" He says, "It's a weld lab." And the safety officer says, "Well, what do they expect to come out of a welding lab?" So that's kind of satisfaction they got, which I thought was good, because it turns out there is no toxicity to the TiO2. It's not a problem, but it's just a little smoke. And, but actually, it's more than a little smoke, it's a lot of smoke. But we did have ventilation. In any case, where do I want to go with that? I'm going with that, but we do want to continue on our cutting.
I have a question. Yeah. You said that you're actually burning more metal, you're burning the iron, you're burning the titanium.
Yeah.
It seems like you're just accelerating the corrosion. And so is that what you're doing? Are you making rust?
Well, you're not making rust, because rust is Fe2O3.
Okay.
Iron has 3 different types of oxides. Fe2O3 forms at low temperatures, let's say below 400 degrees Fahrenheit or something like that. Fe3O4, I don't know, these numbers that it forms at are forms between 400, they're only approximately, let's say 1200 or something. And FeO forms at high temperatures. Turns out Fe2O3 hydrates to form an iron hydrate. That's rust. Orange, brown, nice fresh rust is orange. As it ages, it hydrates slightly differently, turns brown. Fe3O4 is magnetite. It's magnetic, responds to a magnet. It's sort of black. This could be magnetite on the surface of this piece, but I'm not positive. FeO is a slightly darker black. The black iron pipe that plumbers use to plumb boilers and things like that, that's FeO. That's what's called mill scale, because it formed at high enough temperatures that you're getting FeO. It's a very adherent layer. And in fact, you can ask the question, well, why can I use in a boiler, if I go down in my basement and I look at the hot water, or the heater, in the hot water boiler, it's just black iron pipe, it's steel pipe with FeO on it. Okay? If I look at my potable water system, the stuff I drink and wash with and everything else, it's copper. Well, why do I spend the money for copper if I could use black iron pipe? What's the difference between the two systems? Not temperature, yeah, but it's hotter, we make it worse in the boiler, right?
You still get a lot of corrosion in the boiler system, though. And
well, you can.
The water in your boilers is like sludge after a while. So
if you're not controlling things properly, that's true. Okay.
Which is 95% of the homeowners.
Well, I've seen homes that have the same black iron pipes for 50 years.
Oh, sure, the pipes will stay there, but the water in it,
gets rusty looking.
Yeah, it tends to be rusty. It's all
Yeah,
the
but
oxygen
you
in the water.
go cut those pipes open, then you're not going to see too much corrosion. First of all, to answer your other question, if you look at the dictionary, corrosion is a gradual process. This is not a gradual process. It is oxidation, and you can consider corrosion an oxidation process, but a corrosion is a gradual oxidation process that occurs over time, if you look in the dictionary. So that's the lexicographer's answer to your question. But the answer I want to give is that the difference, you only get corrosion in aqueous systems if you have moisture and oxygen. If you have a system where there's no oxygen available, then you won't get corrosion. You need something that'll kill the fish. And so the problem is, in the potable water system, I've always got oxygen in the water, and I'm bringing new oxygen into the system all the time. In the closed system, the boiler system, I'm not bringing in a lot of makeup water. Yeah, I bring in makeup water in my home about once or twice a year. You know, as the changing of the seasons and the walls change their average temperature, the water expands or contracts. I got an expansion tank on my system, right? And so, you know, sometimes I'll have an overflow valve, so if it's warming up in the spring, every now and then I'll go and I'll notice that some water is on the floor because it drained out. Okay, not a whole lot, but basically the system is warming up as the house warms up in the spring, and the water expands, and so the overflow, you get too much pressure, and the overflow valve will let some water out. And then in the fall, which just happened to me a couple of weeks ago, there was something wrong with I was hearing all kinds of gurgling in one of my pumps in the hot water system. It turns out my hot water system is connected to my furnace to do the heating of the hot water, and it turns out that the pressure had gone down. And some plumber had been in there about a year before, and he turned off the makeup water valve. So there's no makeup water. So as things started to cool down a couple of weeks ago, and this water contracted, I ended up getting, you know, basically cavitation in one of my pumps. Anyway, because of the loss, I had air in the system. And we were hearing a gurgling up in the second floor. You could hear a gurgling from the third floor in my daughter's bedroom. You could hear something making noise for a couple weeks ahead of time. And finally, when I realized this guy turned off the makeup water, he turned on the makeup water, and the gurgling on the third floor went away because I didn't have any more air in my pipes. But the problem is, if there is oxygen in the system, then you get corrosion. It's not the water that forms the iron oxide. It's not a reaction of iron plus H2O goes to iron oxide plus hydrogen. It's a question of the water promotes the galvanic reaction somewhere in there that allows the oxygen in the water to react with the iron and cause pitting and other things. You get the oxygen out of the system, you got no corrosion. And that's why in boiler water systems, commercial ones, that they really can't afford to have corrode, they put deoxidants in there. And they put things like nitrites, okay? A nitrite is an NO2, which will oxidize to an NO3. So it scavenges oxygen from the system, and it prevents corrosion. You put hydrazine, which is HN2. Hydrazine will scavenge the oxygen, okay? It's not that, hydrazine itself is not that stable. It will form water plus nitrogen, okay? And so in nuclear reactor water, you basically put hydrazine when you cool down the reactor and shut it down for a while. They put hydrazine in the water to keep any oxygen from getting in the water. The problem, not at 3 Mile Island reactor that had the problem, but the other sister reactor next to it. When they started, they had to shut it down because of all the regulatory stuff until they determined it was safe to turn it back on. When they tried to turn it back on a year, 15 months later, they had major stress corrosion cracking problems because oxygen had gotten into the system. Okay, and as they warmed it up, and hot water will usually corrode faster than cold water. Turns out during the heat up, in a 2-hour period, they did $30 million worth of damage to their steam generator. Okay, it's by stress corrosion cracking of the nickel-based alloy because there was oxygen in the system. And so nowadays, when someone shuts down a nuclear reactor, they do something. They either pull a vacuum off the top of the water system, the closed water system, or they put nitrogen over it, pure nitrogen, or they put hydrazine in, or something to get rid of the oxygen in the system. Because it's the oxygen. You got to have both water and oxygen to get corrosion. So why do we use copper pipes? We use copper pipes because copper has more resistance to oxidative corrosion. And so I'm going to spend more money on my open water system, my potable water system, which has always got plenty of fresh oxygen coming through. What happens when I seal off that closed water boiler system, yeah, there's oxygen there, but I consume it very quickly by forming a little bit of mill scale. And in fact, it's a low pressure oxygen system, and I will actually form this not just at high temperatures, but at lower oxygen pressures than atmospheric. I'll form FeO rather than Fe2O3. Right? Obviously, this has got more oxygen. These two have more oxygens than this. This is going to be favored as the formation at lower oxygen pressures and higher temperatures. So what happens is I scavenge the oxygen by doing a little bit of corrosion in my system. Then the oxygen's gone, and as long as I don't let it back in. Now, about 4 or 5 years ago, someone sent me an 1-inch pipe and says it had complete hardening of the arteries, completely clogged, okay, with rust. And this is from a wet fire water system, which is supposed to be a closed system. Okay, your fire, your sprinkler system. There are dry systems and there are wet systems. The advantage of the dry system is there's no corrosion going on in the dry pipes. The disadvantage of it is if the valves don't open, you don't have any water to go anywhere. The wet system, the water's always there, but the disadvantage is if you don't maintain it properly, you can get corrosion. But it's supposed to be a closed water system. Well, they brought me this thing, and this thing, it was only a 7-year-old system. And they said they had it, I threw it out, but I had it next to my desk for about 1.5 years. It was about a 1-inch length of pipe and just completely filled with rust. And I called them up, I said, you guys got a leak in your system somewhere. He said, well, yeah, how'd you know that? I said, because you got to get oxygen in the system to do this kind of corrosion. He says, oh yeah, well we had this one, it was a big warehouse or something. He said, we had about a 3/4 inch or 3/8 inch leak that we just let it go down the drain for the last few years. Okay? So they knew they had a leak in the system and they had makeup water coming back in. And they said, well, what do we do? I said, you replace the entire system. Okay? Because you didn't fix the leak for 3 years, you now get to replace the entire system. You can't run potable water through an iron system. It will corrode because of the oxygen, right? So that answer your question?
Yes.
See, I told you I can go with one digression. I'd much rather do digressions than this other stuff. Anyway, let's see, you'll remember the stories. Just lecturing is dull. Okay. Do I have any other stories on the water systems? I do have some other stories on water systems. Turns out that if you have soft water, which we have in New England, I told you about marbleizing pipes before, didn't I? That in a potable water system, the copper pipes, you want to have a little excess calcium so that the limestone precipitates out and you get these marble deposits. Because it turns out limestone is calcium carbonate, marble is calcium carbonate, just a slightly different way it formed geologically. But they call it marbling of the pipes. If you have a slight excess of calcium in your water, and calcium is hard water, then you will plate out this white deposit on the inside of your pipes. Now, sometimes it's so thin you can't even see it. If you cut out a piece of pipe from your basement, and you're in an old house around here, and you slit the thing in two, and you look at it, it'll just look kind of brownish copper. That's because the marbleized layer is so thin, you can't see it. But if you put in the scanning electron microscope, and you just analyze that surface, you're going to see all kinds of calcium and copper. I mean, the copper peak might be 5 times the size of the calcium peak, but you'll see a significant calcium peak. The reason being, you basically had limestone or marble precipitate out, if you're lucky. The problem nowadays is they're more concerned about lead contamination in the water, and so they're not controlling the water chemistry to try to make sure the calcium, you have the right hardness, They're trying to make sure that you don't have any corrosivity to the solder and stuff. And so it turns out 5 or 6 years ago I had to go before the state plumbing board because this one plumbing inspector in a town north of here there's people in this brand new subdivision, and they've been there 5 years, and all of a sudden they had sprinklers in their overhead in their living room, and the copper pipes were just springing all kinds of leaks, and you look at them, they're all pitted. And it turns out people were having washing machines go and hot water heaters after only 5 years. These things have like 10-year warranties on them, and they're just springing leaks. Well, this really clever plumbing inspector determined it was defective copper pipe, even though it was occurring in sprinklers in washing machines and dishwashers and hot water heaters that had different types of copper pipe. He determined there was this one company in Chicago that made copper pipe. There's only 5 companies in the United States that make copper pipe. And he was determined to have them barred from doing business in Massachusetts because they sold this defective copper pipe. It was defective because it was leaking. Now the fact is, other copper pipe was also leaking, but you know, he couldn't quite figure that logic out, that his analysis didn't quite make sense. So we did all kinds of tests, and it turns out these people didn't have, if you went and analyzed the surface, they didn't have a limestone layer. So I got to go to the town water department and read through a year's worth of records, and the town had built this wonderful new water treatment plant right next to the little lake there. Okay? Nice soft water in the lake. Water comes in at pH 5.5, nice and soft. They hardened it in general up to a pH of about 8 or 9. But if you looked at the Langeler index, this calcium hardness index, if you looked at the old plant they were always kind of bouncing around between negative 0.5 and plus 0.5. So sometimes you'd be precipitating out limestone, and other times you'd be negative, but it turns out it didn't dissolve away that quickly. But you were bouncing around. In the new plant, with all the great controls they were always at minus 0.3, plus or minus about 0.1. So they had a much tighter control of their water chemistry. Unfortunately, it was negative, which meant you never got the limestone layer. Everyone else in town was fine because their old pipes already had the limestone layer. But the people in the new subdivision didn't. And so their pipes went through in about 5 years. There's some places where people have their own well water, in New England or Michigan or something like that, where they have a lot of salt water, and you can perforate copper pipes in 6 months. Okay? So copper's not the real panacea for open water systems. It's copper with the right hardness level. So that's another thing. Okay, let's finish up on flame cutting. Let me pass around. These are 3 pieces that are plasma cut. There's nothing special about them. This actually is a plasma cut oxy-acetylene wrench for the oxy-acetylene cylinder. So they just took a piece of steel plate and they plasma cut it. Plasma cut can give you a much smoother surface. This is just a test plate of stainless steel. You can plasma cut stainless steel. Plasma cutting is not trying to burn through with oxygen, it's trying to melt through with the plasma arc. So you actually are just melting through, and you can't cut 4-inch thick with plasma arc. You can go to about 1.5 inch, but given the fact that's most of the materials that we deal with, plasma cutting gives a nice smooth surface. There are some problems. I think I passed this around the first day. The corners have some problems because as you come up and the heat flow around as you turn the corners gives rounding or defects at the corners. They're working on that. This is a plasma cut piece of steel done on a numerically controlled machine tool, and you can see they actually had to punch through here to start and then go around the hole. But these things are very nice surfaces, but they just melted through basically with plasma cutting to give you another idea of surfaces. Now it turns out that the reason you can get such high rates of heat transfer, effective heat transfer in here, is because I have no gas boundary layer, in theory. What happens to the gas? Well, the gas in here is pure oxygen, and the pure oxygen, this is a solid, this is a gas, and it goes to a liquid. So I condense my boundary layer to a liquid. The boundary layer is consumed by the reaction and forms a liquid, which is blown away by the hot, by the jet of oxygen coming in. So in theory, if this is the only thing I have no gas boundary layer, and now I can get the whole combustion heat intensity, essentially, of the flame. In this case, the flame is an oxygen iron flame, but the combustion heat intensity is the rate at which I blow that oxygen to the surface. Okay? And so, if I calculate a combustion intensity, it's the enthalpy of this reaction times the velocity at which the oxygen is coming to the surface, and I don't have to degrade it by 90 to 98% because of a boundary layer. I actually have the full heat intensity on the surface. So I go from 1,000 watts per square centimeter to 100,000, or close to 100,000 watts per square centimeter, as an effective heat intensity. And if I look at my heat effective zone sizes and travel speeds and everything else, the effective heat intensity is several times 10 to the fourth and approaching 10 to the fifth watts per square centimeter as an effective surface heat intensity. But it's not really a surface heat intensity because I'm really blowing my fuel down beneath the surface, right? But nonetheless, if I look at these other parameters, it's a very, very high heat flux. The problem is it is actually limited by some other things. Steel is not just iron, and I don't have just iron and oxygen. There's a paper you have called the iron-oxygen combustion process, which is about oxy-acetylene cutting. It's a nice new paper from about 1956 or so, 1955, sorry, September 55. Probably the best paper written on the subject, even today. But in any case, what he did is he has the equivalent concentration. This is oxygen purity plot down here, and this is the equivalent oxygen purity. But if you actually start adding, if you start measuring relative combustion rate, how fast could he flame cut? This is a guy, Alan Wells, who used to be head of the British Welding Institute, but since retired. After all, he wrote this in 55. In any case, if you have, where's his oxygen purity? Okay. Standard oxygen purity was 99.7%. In any case, he's got Fe2O3 as the oxide that forms, or FeO that forms, and he finds that, oh, this is the oxygen. This is the oxygen purity going from 98%, 97, 99% something down to 80% or 60%. And you find your ability to burn, the speed at which you can burn, goes down as your oxygen purity goes down, because in fact now I have excess nitrogen around. I've now replaced something that forms a boundary layer. It's a thinner boundary layer because it's only a partial boundary layer. I have less nitrogen than if it was air. But even a 5% impurity gas, inert gas in my system, so if I go from 99% down to 96%, I'll get about a 1/3 drop in my speed that I can cut with. So you have to use high purity oxygen. Up here, he basically was looking at the fact that if I look at the carbon content, that's what he means by equivalent oxygen purity. If I look at the carbon content, if I have Swedish iron or Armco iron, which has almost no carbon, or low carbon steel, and I go down here to razor steel, which is over 1% carbon, here the effective impurity is the carbon in the steel. Carbon plus 1/2 oxygen goes to carbon monoxide, which is a gas. And the carbon monoxide forms a boundary layer because it's not consumed as readily. So basically down here, it's nitrogen impurity in the air that's dropping my cutting speed. Here, it's carbon monoxide formation because I'm burning the steel. High carbon steels will cut slower than low carbon steels. There is a difference. And it's controlled by it's basically controlled by the boundary layer. So that's what happens with cutting. I didn't say anything else about cutting. Anybody have any questions on cutting? It turns out it's an amazing process to me.
How, the width of your cut and the thickness of the gap that you're gonna get, that's just strictly determined by the fineness of your oxy you get, right?
Yeah, the width of this thing.
Yeah.
I mean, when you're cutting something that's 6 inches thick, or 6 inches thick, you're gonna have a 1/2 inch wide or 3/8 of an inch wide kerf. If I'm cutting something very thin, I can make that down to 1/8 of an inch. I can't get much smaller than that. And if I'm doing something that's, 6 feet thick, I may have a kerf that's 1.5 inches wide, obviously. But you try to cut through 6 feet of steel any other way. Although, we don't have time. I'll tell the next class. Okay, on Monday, I'll remind me to tell you about how do you cut aluminum, if you have thick aluminum. But that's enough for today.